Washington State University. Go Cougs!
The last activity prediction task that we will look at is predicting when a specific activity will occur. In order to distinguish this type of activity prediction with the sequence prediction, we will refer to this one as activity forecasting, because we are forecasting into the future when the next occurrence of an activity will be. So this technique will actually output the delay or number of time units until an activity will occur from the current point in time. Now remember, this feature vector that we extracted from a sequence of sensory events collected by ambient sensors. You can see here that activity recognition has labeled this feature vector with an activity called Enter Home, which corresponds to the video in which the resident entered the home before she started to put away groceries. Activity forecasting will actually use activity recognition to help provide training data. These labels are necessary in order to be able to determine from sample data when the activities do occur, so that a machine learning algorithm can eventually learn when they will occur again in the future. So given the data that we see here on the screen and this particular feature window with the label Enter Home, let's assume that there was an earlier point in time, 9:50 a.m., in which the previous occurrence of Enter Home finished. At 9:51, then, an activity forecaster would ideally determine that the forecasted time for the next Enter Home activity is at 11:42 a.m., as we see here in the data. Therefore, the forecasted delay until Enter Home will occur again is the difference in time between 11:42 and 9:51, or 111 minutes. Now suppose that after this occurrence of Enter Home, the next occurrence later on in time will be at 5:00 p.m. At 11:42, then the correct output for an activity forecaster would be 3,018 minutes, which is the number of minutes that will elapse until the activity Enter Home occurs again. You might remember from the module on activity recognition that from this particular window of sensory events, a feature vector was extracted, like the one that we see here. With activity recognition, we were using a machine learning algorithm to learn a mapping from this feature vector to an activity from a set of possibilities A. The problem of forecasting is a little bit different, because instead of outputting a symbol like Enter Home, we actually want to output a number, in this case 3,018 minutes. So what we can do instead is use a regression learner that will actually learn a mapping from the feature vector to a numeric value D, which represents the time delay before the activity of interest will occur again. How we can train a regression learner is with sample sensor data that is labeled with events by an activity recognition algorithm. The training data then acts like an expert that's demonstrating the prediction task, because if every sensor event is labeled with a corresponding activity, we can use past data to determine for any given data point how much time did elapse until the activity occurred again. Therefore, with every data point, we also have a specific amount of time that elapsed until an activity occurred again, and we can learn a mapping from the data point to that value, the delay value. So our regressor needs to emulate this trajectory. So in essence, it has as input the observed delay that it can use to train a regressor and the input feature vector. To learn the mapping from the feature vector to this actual observed delay, this ground truth, we can employ any regression learner. Some common ones are linear regression, logistics, support vectors, neural networks, and regression trees, or a forest of regression trees, which we have used with success in the past. With a regression tree, it looks quite a bit like the decision tree that is discussed in machine learning classes, including the one that is available as part of this program. So like a decision tree, each one of the nodes in the tree will query a value of the feature vector, and depending on the outcome of the query, the path would go to one of the children. However, unlike a decision tree, the leaf nodes at the bottom do not give us a class label. Instead, each of the leaf nodes is actually a linear regressor that is just using a portion of the features to regress the data and thus be able to map the feature vector to a value indicating the delay. Once again, in order to prevent overfit, instead of using a single regression tree, you can use a forest of regression trees. Let's consider two enhancements that we can add in order to strengthen the ability to map feature values onto a numeric value D, indicating a delay until an activity of interest will occur again. The first is that we can add lag values to this feature vector. With a lag value, we assume that we have actual delay values for a specific activity for earlier data points, a fixed number of data points, and we will refer to that fixed number I as the lag, and that's the number of earlier data points for which the actual delay value is available. They may not correspond to previous sensor events if that delay is not known. They may correspond to sensor events that occurred a while ago. We can add the lag values to the feature vector as we see here. In this case, there's a lag of 3. By adding a lag, we begin to get a pattern of the regressed values over time, and that can actually enhance the ability to forecast the delay for future time points. A second enhancement that we can add is to add predictions that we have generated for other activities to our feature vector as well, in a process that we refer to as joint prediction of multiple values. In this case, what we do is use our training data, our feature vector with optional lag values, to independently learn forecasted times for a number of activities of interest. As we show in this diagram, we could be learning delay values for the eating activity, a take medicine activity, and a sleeping activity. Each one of these forecasted values, or these learned delay values D, are then added to the feature vector for a second round of regression-based learning, in which we update the forecasted time for eating, take medicine, and sleeping. The justification here is that the relationship in time between different activities can be very important in determining when an activity will occur. For example, an individual might wake up and immediately eat, and after eating, immediately take their medicine. And so if we have a robust predictor for learning the delay until an individual eats again, then that value can be used to enhance the prediction of the delay for a take medicine activity. As before, the training data acts as an expert that's demonstrating the prediction task, but with these two enhancements, our feature vector has more information now. It includes all of our original feature, plus the lags, plus the forecast times from each of our individual activities. All of this is used as training data, and the output of this second pass at prediction is a multivariate output, or a set of predicted delays for the entire set of activities. Let's consider how to evaluate activity prediction when you build your own activity predictor In the case of the first prediction task, where we are predicting what activity will occur next in a sequence, we can use an accuracy measure as we did with activity recognition, because the output is a specific symbol indicating which activity is going to occur next, and it's either right or wrong. In the case of activity forecasting, where we are predicting a delay until a specific activity will occur again, we might want to consider other measures, because while it might not predict the absolute number of minutes correctly, it could be quite close. So another evaluation measure is one like mean absolute error, which is the absolute value of the difference between the predicted time and the actual time. As we see here, if we're looking at an activity enter home, and the red lines indicate the actual delay until the activity will occur again, and the blue times indicate the predicted time until the activity will occur again, then for any time t, what we want to look at is the difference between the blue line and the red line, and that is the error. So it's the absolute value of the difference between the predicted delay and the actual delay. When you look at this, you can see that this is kind of a daily activity in this particular case, and the forecasted and actual time becomes 0 when the activity occurs, and then it spikes up high right afterward and slowly starts to get smaller until the activity occurs again in a cyclic pattern. So we want the blue and red lines to precisely overlap in order to minimize this error. Another evaluation measure that we could use would be an error threshold fraction. And this would be the case where we have specific tolerances of error for an application, in which it might be important to be correct down to the hour, down to 10 minutes, down to the minute, or even down to a number of seconds. In this case, we can look at the fraction of errors that occur below a specific time threshold as an evaluation measure. Now let's briefly look at one application that uses activity prediction based on ambient sensors. And this application will be discussed in more details in the next course of health applications of behavioral analysis from ambient sensor data. This particular application is called a digital memory notebook, and the goal is to improve everyday functioning and to compensate for problems caused by memory loss, as might happen with individuals who have traumatic brain injury or are aging. A digital memory notebook follows on years of tradition in which pen and paper memory notebooks were used for individuals to journal their thoughts, to write down activities that occurred that they can refer to later in order to help their memory, to store names and birth dates and important events, to make appointments and to-do lists. With the advent of digital devices, now we can use this interface to make a notebook that's digital and a little bit easier to use with an interface as we see here. What makes this particular digital notebook of interest is that it actually interfaces with the smart home and ambient sensors, uses activity recognition to check off important activities when they are detected as being performed, and it can also prompt individuals for activities that they need to perform. As we see here in this interface, each activity that the individual wants to track and make sure that they complete is listed along with the time that it was detected by the environment using ambient sensors, that they can either confirm or leave blank if they are disagreeing with the home. And that way, individuals who have memory problems and are anxious about whether they're performing important activities or not have that confirmation, and they can refer to the notebook to make sure that it has been done. In the case of activity forecasting, it can be integrated into this intervention or this digital memory notebook by including information on when important activities should take place. And so this interface will indicate the predicted time when an activity should be performed and can be color coded depending on how close in time we are getting to when the activity should be performed, and even deliver a verbal cue in order to prompt the individual to initiate the activity if it has not already been detected using activity recognition. This is the end of the course on activity learning from ambient sensor data. Please look at the other courses so you can learn more about how to use all of these techniques for health analysis and intervention, and also look at the courses on activity learning from mobile and wearable sensor data.